Hi, welcome to Practical Skills for Making Stuff with Electronics. I'm Tyler Bletch with Duke University. This is part one of a two-part video series. This part covers sensors, modules, and actuators. If you want to jump to a specific subsection, you can find timestamp links in the description. These videos assume you already have a basic introduction to breadboards, voltage and current, and either Arduino or Raspberry Pi or another microcontroller. And these videos are designed to serve as kind of a jumping off point in your investigations of different pieces, components, and techniques you can use when building larger projects. The idea here is we're going to help you integrate electronics into your design so you can move beyond just simple passive machines. Give you pointers to understand the design space. What is the universe of components and possibilities out there that are commonly available? And give you lots of good practical advice to avoid the most common rookie pitfalls when getting into this kind of engineering. Using these skills, you can build things like robots, home automation, toys, musical instruments, and many, many more kinds of things. So let's dive right in. Here we have a map of a thing, whatever kind of thing you want to build. It's going to have some sensors probably to learn things about the outside world. It might have some what we call here digital modules, maybe some form of communication like Bluetooth or Wi-Fi. And it might have some actuators, motors or similar things to do work, push things and do things in the real world. All those things are going to be hooked into with some wires into some connections into your controller, some either Arduino, Raspberry Pi, some other kind of control or logic system. You'll probably have some kind of human interface. This could, range all the way from like a touch screen or display with buttons, all the way down to something as simple as an on-off switch, which you probably want to have in any case. All of these things are going to get wrapped up into some kind of physical enclosure or frame or chassis, some kind of physical thing to hold all this stuff. These videos will touch each of these areas and give you options and tips in each one. In particular, let's look at an example to understand how these components might fit together. So let's say we want to build an automatic plant watering robot. Something's going to water our plants for us. On the sensor side, you might have a soil moisture sensor. There's one shown there. That'll tell you how much hydration is in the soil to know when to water. You might have a Bluetooth digital module so that your robot can talk to a phone or some other nearby thing to let you know what's happening with the watering. You'll have some kind of actuator, maybe a DC motor driving a pump to pump water onto these plants. All those things will get hooked into a controller. For example, an Arduino Nano is a reasonable choice for this. You might have some accessory chips and stuff, so you might solder the whole thing together onto a piece of proto board. A piece of circuit board that you can connect various things together in a free-form way. You might wrap all this stuff together in a 3D printed enclosure, for example. And for your interface, you might use what are called panel-mounted controls, such as shown here with some switches and knobs visible on the front, all held in a box. This is an example walkthrough of how we might fill each of these categories up for a practical device. If we come back to our overall map, this video will focus on just the first three things: sensors, digital modules, and actuators. And the second video will cover everything else. So let's dive right in. And remember, this video is intended to just give you places to investigate. You're not going to learn everything about any one of these topics in this video. It's to let you know the universe of options for you to investigate more fully. Looking at our basic sensors, the most basic one is a button or switch. Just a very simple thing. Is this being touched? You obviously recognize buttons from the world, things you press as a human, but buttons can also be used in your mechanisms. For instance, if you have some kind of moving carriage or other mechanism, you might have a limit switch shown here that will tell the machine when that moving carriage has reached one of the sides. So if you just need to detect simple touching, buttons are where it's at. Two tips on using these: you'll need to do what's called debouncing. Basically, when you touch a button, it doesn't just close the circuit. It actually wiggles at a very, very small time scale, and the microcontroller could detect that. So there's techniques you can do to fix that. The other thing is you'll probably want to use what's called a pull-up resistor. That is something to hold the voltage high until the switch grounds out that voltage. You can learn more about these by reading online tutorials such as the one linked here. You can access these links by downloading the slides linked from the video description. Also, the links themselves are also embedded in the video description. Moving on, we go from simple button pressing to what if you want to know if something has rotated up to a finite maximum. Think of a volume knob. For this, you can use a potentiometer. This is an analog input, and you'll just connect the outer legs of it to power and ground, and then that middle pin you can connect to an analog input to your microcontroller. And this can measure a voltage between 0 and the full voltage of whatever your circuit is. These come in many, many flavors. You can see here there's regular turning potentiometers. There's slide potentiometers. There's little tiny ones called trim potentiometers. There's even multi-turn potentiometers where the knob turns not just one rotation but multiple rotations. But all of these go up to a specific maximum. So for instance, if you have a rotating arm and you want to know how far the arm is rotated up or down, a potentiometer on there is one way to do this. You can find a tutorial linked here on how to get into using those. Another way of detecting rotation is an encoder. An encoder allows you to detect continuous rotation. So think about the fancier volume knob on modern car radios where just click, 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 and you can just keep turning that thing up forever. That's a mechanical rotary encoder. Encoders use two waves of high and low values to indicate ticks of rotation, discrete angular units of rotation. You could think of these as a human interface device to click up through options in a menu, or in a mechanical system to measure continuous rotation. For instance, if you're building a robot, you could put an encoder on its drive wheels, so not only can you tell it to go, but it'll know how far it's gone. You can find information on the link tutorial on using encoders. If you want to detect the presence of something without actually touching it, a simple, cheap way to do this is a Hall effect sensor. These can detect magnetic fields up to around 10 millimeters or so, and they work just like a button. You hook them up like a button. They're a simple chip form factor, and with cheap magnets glued to whatever the thing you're working with is, you can detect something without actually touching it. So if you have a moving carriage or some other motion thing and you don't want to have it physically hit a button, you can have it passively detect that it's made a connection just by detecting an attached magnetic field. Information on using these is linked there. There's many, many more sensors than this. There's a whole family of range-finding sensors, some based on ultrasonic sound waves, echolocation, some based on the time of speed of light. So you can detect how far something is. So you could do simple presence detect if someone is standing here or use your robot approaching a wall. You can detect motion of people and animals using motion sensors, PIR sensors. These are inexpensive. These are what you see in the security motion sensor domes you see in buildings where when you move, the light turns on. These are simple, easy to work with. They emit just a simple yes or no signal. You can have flex sensors. These sense flex. So for instance, you could put these in a glove and detect human hand gestures inexpensively. You could measure the weight of things with a load cell. This is what's inside of digital scales. So you can buy a load cell kit, comes with it with the control electronics, so you can detect weight or pressure easily. You can detect light in a variety of ways: photoresistors, phototransistors, even full infrared sensors that are designed to filter exactly the things that TV remotes emit. So if you want to respond to the signals of a TV remote, you can do that inexpensively. If you want to detect something without touching it, but it's going to be further away, look at your light detection based sensors. So there are sensors specific to detect reflection and also beam break. Think of when you walk in a store and the ding-dong sound goes off. Oftentimes that's because there is an invisible beam of infrared light that's being interrupted by your body. There are kits to do this that are fairly inexpensive. You can even go up and get a full inertial measurement unit. This is an integrated circuit that combines an accelerometer to measure acceleration, a gyro to measure rotation, possibly a compass to measure magnetic field, maybe even a pressure sensor for altitude. And there are modules that actually integrate all these things so that you just have a chip that knows which way it's facing, knows if it's going up, down, left, right, how it's rotating. This is how your phone knows which way it's oriented, is with one of these modules. Now that last device, the inertial measurement unit, is an example of a digital module. So there's a whole world of digital modules that you talk to, not with simple yes, no, or analog voltage levels, but by a communications protocol. Two other digital modules that you might find useful is an SD card reader. So SD cards are cheap. They have gigantic amounts of storage. As of this video, there are 1 terabyte SD cards available in the market. And you can hook up to these fairly simply. SD cards speak 2 protocols, a fancy high-speed protocol you don't want to worry about, and then a much simpler low-speed protocol that you can use for logging of data. So if you want to have a sensor that you stick out somewhere with a solar panel and have it record things for 2 weeks, it can just spin it all out to an SD card that you come pick up later. Another digital module that could be useful is a Bluetooth serial module, such as the HC06. This module allows simple serial communication, in the same kind that you might communicate with an Arduino on a computer to any attached computer or phone device. This can be useful for connecting to phone apps or computer-based interface controls wirelessly. At this point, we need to pause our discussion on sensors for a moment and get a little bit into digital signaling. If we're going to talk to these modules, you have to know a little bit about how you talk to them. Now, in most cases, you'll find an existing library or toolkit that'll enable you to communicate without worrying about the fine details of the protocol. But in terms of wiring these things, it helps to know at a high level how they communicate. There are 3 common general purpose standards for communicating with digital modules: serial communication, the serial peripheral interface, not to be confused with just plain serial, and I2C. You might think, well, I've heard of lots of other ways of signaling. I've heard of USB and serial ATA and all kinds of other stuff out there. Those are pretty complicated. You could do them if you want to, but for most things, early projects as you're getting into this stuff, the serial, SPI, and I2C protocols are good places to start. So let's talk about the serial protocol. Serial is incredibly old. We've been sending signals over what's called the serial protocol all the way back to the Apollo moon lander. It's evolved a bit since then, but it's simple one-way links. You have a wire called transmit that goes to a wire called receive, and vice versa, a wire on your side called receive that goes to the other side's transmit. All they have to do is both sides need to agree on a baud rate. That's basically a rate of bits per second. And there's a few other settings, but no one's cared about them in 10 years, so pretty much baud rate's all you gotta agree on. 9600 is a common default. You'll see this in Arduino come up as default. And if you want to go fast, 115,200 is the common fast rate. You might wonder, why are these numbers the way they are? Don't worry about it. There's lots of weird historical reasons why these numbers are chosen. Just know those are common choices for signaling in serial. Serial is how the Arduino talks to a host computer. It's serial over USB. Anytime you want to have a communication between a microcontroller and a computer, typically a larger system, serial is a good, simple choice. The link tutorial will get you into various forms of serial signaling. Let's shift now from talking about digital modules to ways of actuating, putting force into the world. If you're just coming into your first robotics or electronics project, probably one of the simplest forms of actuator is a brushed DC motor. If you've ever played with a basic motor in a class or as a hobby, these are probably the ones you've messed with. These are motors where if you put a voltage across them, it spins. That's it. Now, in terms of mechanically, these kinds of motors like to spin very fast, but not very strong. That is, they'll go wee, real fast, but if you grab the shaft, you can stop it easily with your fingers. That may not be what you want out of your actuator. And so for that, you'll need to trade some of that speed for more torque, rotational strength. The most common way to do this is with a gearbox, a set of gears that increase the torque output of a motor. Now, this might sound complicated, but the good news is you can buy integrated motor plus gearbox units. These are commonly called gear motors. There's two common models of this shown here, the N20 and the more generically named yellow motor. As of this taping, these are both very common. You can find them on Amazon, eBay for direct import. They're commonly used in hobby applications. If you need higher power than these smaller scale motors can then put out, you could get fancy and talk about building a gearbox or speccing a gearbox from an industrial vendor. But the easiest thing to do is to find a vendor that has an ecosystem of motors and gearboxes. For instance, Vex Robotics is a common vendor for this. What's shown here is an Vex Robotics motor with a Vex Robotics Versaplanetary gearbox that you can actually configure at purchase time to give you the torque that you need. So if you need some heavy-duty torque power, this is a simple combination that can give it to you. Now, how do you drive these things? You do not just hook them straight up to your microcontroller. That's no way to live. You're going to need some kind of motor controller, something that can deal the heavy job of pushing large amounts of amps with a higher voltage to these motors than your small microcontroller can manage. You commonly can adjust this speed using what's called pulse width modulation, or PWM. And these motor controllers are typically what's called an H-bridge circuit, which is a particular arrangement of transistors so that you can ask the motor to spin forwards by applying one polarity or backwards by applying the reverse polarity. You can find lots of tutorials online on using this kind of thing. Arduino has multiple standard motor shields that integrate all the motor controller stuff to them with libraries that you can use. So you can dig in there, research these things, and start spinning some motors. Now, if you have fancier movement needs than a brushed DC motor can get you, you can look at some other options, including a brushless DC motor, or something called a BLDC motor. These motors have 3 or more wires coming into them, and they are run off of actually an offset sequence of sine waves for power. Again, that might sound complicated, but the good news is there's modules to do this for you. You'd almost always pair a brushless DC motor with what's called an ESC, an electronic speed control. Think of this as the motor controller, but for brushless DC motors. A common use of these brushless motors is what you find on drones for the rotors. Like brushed DC motors, they typically want to have high speed, low torque, although with brushless motors, you can get models that have larger amounts of torque out of box without putting a gearbox on them. Using these is a bit more complicated than a brushed motor. You have to care about if it catches and all kinds of stuff. If you feel this is necessary for your project, dig in, do some research. It's totally doable. People use millions of brushless DC motors every day. Now, what if you need really, really precise movement? You need to move exactly 42 degrees clockwise. For that, you might want to look at stepper motors. These are pulsed, you pulse discrete coils inside the motor to cause it to step, tick, 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 specific units of rotation, and they're driven by a stepper driver, a commodity circuit you can buy and add. Stepper motors are what you find in 3D printers. It's how most 3D printers know how to move the head of the 3D printer an exact distance because they move the pulley an exact number of degrees of rotation. Lastly, I should mention that there is such a thing as what's called AC motors. These are typically larger motors that run off what's called mains power, the power outlets you find in the wall. They're cool, they're very powerful. If this is your first electronics project, you probably don't want to mess with wall AC power at all, so I'd probably put those aside for now. So let's say you have your motor. It's spinning a metal shaft of some kind, and in your other hand, you're holding some kind of thing that you want to spin. Your goal is to have this motor spin this thing. How do you do that? You'll need some kind of coupling. You'll need some way to connect your thing, shaft, axis, whatever you're doing, to the motor shaft. To do this, you might want to understand a little bit about how motor shafts are built. Not a lot. I'm not going to go into super great detail. Just knows a few common flavors. The most common at a small scale is a tiny round shaft, where it's just perfectly round. You might think, how am I going to grab onto a round thing? A common way of doing this is with a coupler with what's called a set screw. As you see in the diagram, you have a sleeve of some kind that goes over the shaft, and there's a screw that drives into that sleeve and presses on the side of the shaft such that friction couples it to the shaft. So you could have what's called a shaft coupler, where one side bites into your motor shaft and the other side bites into whatever your mechanism is, and now you're moving your mechanism. There's other kinds of shaft as well. Some shafts are what are called keyed, meaning that they have a little slot taken out of it that you put a bit of metal in. This is a way to transmit even more torque or rotational force. And then there's non-round shafts, hexagons, squares. These can be simpler to interface with because you just need to, for instance, 3D print or otherwise fabricate something with the correct kind of hole that can slide on there and just naturally transmit force. Think of turning a nut with a ratchet or something. That's what you're basically doing. If you need to transmit rotational force in a more sophisticated way, you can look at gears and pulleys as objects of research. Now, there's one special family of motor that's really useful to the starting project engineer, and that is servos. So a servo actually combines several of the things we've already talked about into one box automatically, so you don't have to think about it. A servo is a combination of a brushless DC motor, a small gearbox, and a potentiometer to measure the amount of rotation. What servos do is you can send them a signal basically saying, rotate to 37 degrees, and the output shaft will rotate to that fixed target. So servos do not rotate continuously in general. They're used to sweep specific angles. Think of them as the opposite of a potentiometer. Potentiometer, you turn a certain angle in its range and you read a voltage. A servo, you tell it what angle to go to and it moves there. Servos are really common in robotics. You can have walking bug leg robots. You can have, they're very common in wireless RC airplanes. So the flaps that control the movement of the airplane are lifted up and down by very small servos. The two most common introductory servos are shown in the upper right here. The little blue one is commonly called a 9G servo. It's kind of generic at this point. Many manufacturers make it. It's like a little tiny, very cheap servo, very low force. The one on the left, there's many ones that look like the one on the left. But at the lowest price point, they're all kind of the same. They're all metal gearbox, larger black hobby servos. You harness these by attaching what are called horns, little plastic attachments that you can then connect those to your larger mechanism. So let's actually take a look at a real servo in use. So here we have a fairly generic 9G blue small servo. It has an output shaft here, onto which I've attached this white plastic horn with a screw. These kits come with a variety of horns you could attach for different purposes. The design of the horn was originally intended for you to attach metal wires to the flaps of your airplane's wings, but obviously you can use these things for whatever you want. So what I've set up here is a small test rig so we can try out this servo. This is straight out of the Arduino servo demo tutorial you could look up. We have an Arduino Uno with power going to this breadboard. This breadboard is only used to send power various places. Power is being sent to the servo on its ground and plus wires here, with the signal for the servo coming from pin 9. And we have a potentiometer we've added that's plugging into analog port 0 and getting power from here. If I attach power in the form of USB, the software on here is called the Arduino knob demo for servos. So what I can do is this potentiometer is set to control the servo's angle. So by adjusting this, the software translates that into commands to the servo to set it to whatever angle you want. Now, servos, of course, need not be driven by a potentiometer, but by any software choices you make in the Arduino. So we've covered a lot of sensors and modules and actuators. So where do we go from here? First of all, if you're confused, if you don't know how to build something right now, good, that's working as intended. It's time to read more, do some research, experiment, get some parts in your hand and play with them, prototype, hook some things together, and break things, make mistakes, have it fail, learn the hard way. That's the quickest way to learn. Eventually, you can move towards a proof of concept that you're happy with, and then it'll start to become time to make it real. You'll have some things on a table that kind of do what you want, and you want to put them all together. That's what we'll talk about in the next video. How to connect things permanently, add an interface, add an enclosure, and kind of finish up, pin up your project. Hope to see you then, and thanks for watching.